always having to go back through a table. So we'll have to do a little work now to save ourselves some time later. Work hard, not smart. That's In Unit 6, we're going to start designing columns for different types of lengths and loads. I'll walk you through example 1, which I'll explain the different equations required to design for allowable loads for different lengths and beam sections. And then in a separate video, I'm going to walk you through how to create a calculator and design a table so you can quickly select the right beam selection for the job. So per usual, we're going to start with example 1 and fill out our givens, and then I'll walk you through the math on each of those points. So we know we have a beam, reading example 1, we know we have a beam of 14 feet long, and the beam section is a 10 by 49. I've sorted this by weight, so you should just have to scroll down until you find the 49. And then we'll jump over to our table. I have standard beams W, and we'll just quick sort for W10s. The X in this list is some special character, so you can't just simply type an X and have it filter for that. So we're just going to do W10, and that should narrow it down plenty for what we're looking for. We know we have, here it is, it's a 57. Let's see if this works. I'm going to do 57 J and M. So our radius of gyration X is equal to, that's not going to work. So I can just press equals. Where's our X there? That one. And then the other one was an M, so I'm just going to do this real quick. All this is unnecessary, I'm just playing around. Okay, so we're going to select the minimum radius of gyration because we want to basically design around the weakest axis in terms of buckling. So that's what, let's scroll up here for a second and read. If you want to read a little more on that, that's your slenderness ratio. So you're going to select the least radius of gyration. So when it comes down to it, we know that at its weakest, it's still going to be able to take on that load. So let's put, so you can just either just type that in again, or if you want to, just so you know it's there, which I've used plenty in my time using Excel, you can use the min function, and it'll just select between the two. So if you had a bunch of them, you could just do min, or if you knew it was going to be swapping in and out, the min function will always select the least number. Our effective length factor, K, is kind of, you can find those in this table here. That depends on how the beam is being supported. So this is kind of blurry, but our K is going to be 1 because it's, let's see if I can find that one right here. So it's, yeah, this is almost impossible to read. No, it's this one. This is the one we're using. It's a rotation fixed and translation fixed, but both the C and D do the same thing. So all the problems are going to be 1, but just know that the K will be determined on how the beam is being supported. Our modulus elasticity, since this is still going to be A36 steel, will be 29 million. Let's see if I hit enough zeros. I did. And then our minimum yield point, which is listed in this table here, our FY, minimum yield point, is for A36 steel is 36,000. And then our CC, which I should probably write that in there, that's our column slenderness ratio. For A36 steel is 126.1, or our equation's right here, which just to show you that is what it's going to be. I'm going to press equals square root of 2 times pi, close the parentheses since pi is a function, squared times our modulus of elasticity divided by our minimum yield point, and then close parenthesis. And as you see, it's 126.1. It looks like I got a little sidetracked and forgot to put in our beam section area, which was, again, that was just right here, so 14.4. So let's plop that in there. And we're going to start calculating all the variables to determine what our maximum load would be for this beam section and that length. So our KLR is just that. It's our K times our length divided by R, our radius of gyration, the minimum one. So that's a pretty easy one to do. Our K is just 1 times our length, which we are going to want this in inches, so we'll multiply our length times 12 and divided by our minimum R. Just to reiterate, you want your length in inches because your radius of gyration is in inches, so keep your units the same. As you can see, we matched up with what was in the text, so now we're going to do something a little different than what the text said. The text has you go into a table and find this number, but there's an equation to solve for it for your factor of safety, so we'll use that. So especially like thinking about our calculator, you don't have to go look through a table to find your factor of safety. It's just something that gets quickly calculated off of the all the variables you have for input. And that equation is up here. There are a couple different cases to consider when designing for, well, we're not there yet, but for our FA, the actual stress. And right here at column formulas, that kind of explains what each case would be. So yeah, like KLR exceeds CC, KLR is less than CC, use this equation, and so on and so forth. So we'll mostly be focused on this one here, but know that there are some instances where you might need to use a different equation depending on your situation. With our KL over R calculated, now we can do the equations for factor of safety and axial stress. The text has you run through a table to find the axial stress. We're actually going to put in the equations, so when we do our calculator and all the equations and conditional formatting for our table, we don't have to do something like that every time. You have to just go through and look through a table to find what you're looking for. So let's start with our factor of safety. And the equation's right here. Factor of safety is going to be equal to 5 divided by 3, which that's just a constant, plus 3 times our KLR times, and that divided by 8 times our CC. Then minus our KLR cubed divided by 8 times CC cubed. Yep, and that, now our next step is to plug that number into this equation up here, and it should, when we're done, come out close to what they have here. So we're going to press equals, parenthesis, 1 minus, and I'm just going to use more parentheses than I really need, which is just to kind of keep track of things, because this is kind of a long equation. And that is squared divided by 2 times CC squared, close parenthesis, and then one more. All that times our yield point, minimum yield point, then that divided by our factor of safety. That came out in pounds per square inch. We need that in KSI, so let's divide that by 1,000. And once again, it's not going to be, yep, it's pretty close. Just a little different, just probably because of some rounding things. And then to solve for our maximum load, or our allowable load, we're going to take our stress here times our area. Times area. And that came out pretty dang close to what they had in the example. So as I said, I'm going to make another video here showing you how to set up your calculator and your table so you can quickly and easily complete the problems.